top push button for reset and the bottom push button for start. So let's first do the reset, and then if I press the start, the LEDs will glow. So I have pressed the push button at least for 1 to 2 seconds, and then all the LEDs are glowing. That means some output is coming, but we cannot distinguish the we cannot actually see the results here because of the high frequency is there. Okay, in the previous tutorial we have shown that how to use Vivado for simulating a Verilog source. Now in this tutorial we are going to show that how to implement a Vivado source file. So let's open Vivado again. Opening our previous tutorial. Okay. So in the previous tutorial we have shown that this preemphasis underscore top is our main module. Here we have seen that this main module has three submodules. One is start signal generation, another is input memory, and another is preemphasis, which is the major block here. We have also seen that start signal generation block is actually generates a single pulse from a rectangular pulse, which is actually pressed by a push button. Input memory block stores the input data, and these are the control blocks to read the data from the memory. So we have simulated this design in our previous tutorial. Now we are going to implement it. So before implementing, we have to do the very first job, that is setting the FPGA target. To do that, we have to go to settings, and here we have to set the target. So first we select general purpose, then we have actually RTX 7 board, so select RTX 7, and from here we have this part, and speed crate you can select -2. So -2 is actually higher speed than the -1, and -3 is more higher speed. So I am selecting -2 here, and this is our board. So we are actually selecting this. Now click OK. So our target is set. Now we have to implement this design on the target. So first thing we will do that we will create a constraint file. So what is a constraint file? In that constraint file we will write that which FPGA pins are connected to our signals. So we have actually three input signal. One is clock, another is reset, another is start, and one output vector. Output vector is of 16-bit width, which is LED. So let's add the constraint file. It is actually added here, so I am actually showing you by deleting it again. So remove from this file, and again you can add this by here, add create constraints, add files, and this is the file I have written previously. So I am adding this constraint file. So let's see what is inside this file. It is actually uh, .xdc file. Name can be given anything. I have given it is vpc underscore xdc. Let's open this file. So in this file there are many things written. So uh, first signal that we have to worry about, that is clock signal. So this is our input clock signal, and this is connected to N11 pin of the FPGA, and this is the IO standard LV CMOS 33. So this is the clock signal. Then coming to the reset signal, which is uh, defined here for the push buttons. So using some push button, we are going to give reset and start signal. So for reset, K13 pin is selected. For start, L14 pin is selected. And for the output vector, we will select these LEDs. So here 16 LEDs are there. So let's uncomment this also and make it LED because it is capital. I think it doesn't matter, but I have to make it all small. So after making this file, our job is done for the implementation. So now we have saved this file. So we have defined port for clock, we have defined port for output vector, we defined port for reset and start. This is very important file to implement this in any source file in FPGA. Without this, there will be no output on the FPGA. So PMPSys underscore top is the top model. So before going to the implementation part, let's again do the simulation. So click on the simulation, run behavioral simulation. So let's see the output again. Change the radix to signed and see first output is 1232, second output is -2633. Okay, now let's close this simulation part. Just note the output, it is 1232 first output, second output is -2633 because we are gonna need this output. So closing the simulation. Okay, now our first job to do is to run the synthesis. So it will take some time to do the synthesis part. Okay, it's completed. Now our first step will be click on the run simulation and run post synthesis functional simulation. This simulation is very important. This is the simulation we are doing after synthesis part. So why we are doing this simulation? So basically the behavioral simulation and post synthesis simulation should give you the same result. Otherwise, your architecture has some uh, faults, or it some portion of the architecture might be optimized. So we will see whether the output is same or not, and again change the radius. See, output is same. So if the output is not same, we can say that the uh, something is wrong in the architecture. So once we verified this, we can say that our almost maximum job is done. So after verifying this, we can close this here, and after synthesis, so we can see this is the schematic generated by Vivado. This is after synthesis schematic. So don't mix up with the schematic that was resulted in previous tutorial. That was the elaborated schematic. So elaborated schematic and post synthesis schematic can be different. It is based upon your design. If Vivado optimized something, then then uh, those logic which are optimized may not be seen in this design. So here see, all the blocks are present, and I can open the preemphasis part. Here you can see, so in the rest 3 part you can see this is the DSP block used for multiplication. So DSP block is used for multiplication, and you can see here that the adder part is actually implemented here by the LUTs. So Vivado actually combined some of the blocks. So now we can go for the implementation. So our next step after synthesis is the run implementation. So if I run implementation, then again it will take some time, but after that our implementation part is almost ready. So implementation part is completed. Now we'll go to the generate bitstream part. So it will generate a bit file, and that file is going to be loaded to the FPGA. So bitstream is generated now. I will open the hardware manager, then open target. Okay, before that your FPGA should be connected to the your connected to a PC, and in that FPGA board some light will be shown that it will indicate that the FPGA is working. So in my board presently is red light is glowing, that means it is working, and it will automatically show this option. So now I will do the auto connect. Okay, now my I have to do the program device. So this preemptive top.bit file was generated after bitstream generation. Now I have to program this file to the FPGA. So after programming, one LED will also grow, that will show that programming is okay. Now let's see the implementation on the FPGA device. So I have selected the bottom push button for let's see again the top push button for reset and the bottom push button for start. So let's first do the reset, and then if I press the start, the LEDs will glow. So I have pressed the push button at least for 1 to 2 seconds, and then all the LEDs are glowing. That means some output is coming, but we cannot distinguish we cannot actually see the results there because of the high frequencies there. So this is all about the implementation part. Okay, now let's see the implementation results. So I have selected the bottom push button for let's see again the top push button for reset and the bottom push button for start. So let's first do the reset, and then if I press the start, the LEDs will glow. So I have pressed the push button at least for 1 to 2 seconds, and then all the LEDs are glowing. That means some output is coming, but we cannot distinguish we cannot actually see the results here because of the high frequency is there. If I open the implemented design, then I can see that some results it will show. That means the performance of the architecture will be shown here. So it is showing host negative slack or WHS, all are not applicable. It is also showing timing constants are not met because I haven't specified any timing constant in this XDC file. Only hardware constants are mentioned. Timing constants are not mentioned. To mention the timing constant, I have to uncomment this line. Let's apply some clock period here. Let's say 5 nanosecond I am applying, and this is the half period. So 5 nanosecond is the clock period, and 2.5 is the 1 period. So this frequency I actually want to achieve by my design. So I will again do synthesis and implementation. So again I will run implementation. It will again take some time. So it's completed. We did not generate the B stream again. So what we do, we will reload. Okay, now we can see the implemented designer open, and you can see that it is saying that all user specific timing constants are met, because we have given some timing constant and it is met. So at which frequency it is operating now? We can say 5 nanosecond clock period. So it is 200 megahertz, and you can see WNS is 2.824 nanosecond, and WHS is 162 nanosecond, and it is host pulse with slack is 1.728 nanosecond. So we can say it is saying that we can go further to achieve the more high frequency. That means I can reduce the clock period further, and if we go further and further, and we can see that at some point this will say that your timing constant is not meeting. So at some point we can say the so this way we can achieve the maximum frequency of a design. So at this frequency we can measure power here. So it is say or loosely the dynamic power of this design, though this is not the actual dynamic power because we haven't considered many things here. So this is approximately this is the power, and your clock signal is consuming this, control signal is consuming this, logical is this, DSP is consuming this, and IO is this. Total breakdown is shown here. And your reports, if you want the utilization reports, so go to place under place design, we have to go to this report utilization. So in this design you can see that this is a slice logic consumption report. Slice LUT 41, slice register 56, and this is a distribution of slices, and we can see uh, memory consumption here. So memory is not consumed here because this memory is actually implemented by the LUT, because it was small memory, so it was implemented by LUT. That's why no RAM blocks are consumed. And this is one DSP block is consumed to actually implement the multiplier that I have shown in the schematic. So one DSP block, 0 RAM block, and this is the slice logic application. This way we actually analyze the performance. So what we have analyzed? Hardware complexity and timing complexity here. So in this XGC file, if you want to achieve more than this frequency, we can decrease it further, like 4, 5, or we can again give it here 2.25. So this way we have to again do the implementation, and if the timing constant is not met, then again we have to change the clock period here. So this way we have to calculate the maximum frequency. So let's end this session. In the next session we will discuss how to verify a design which is implemented on the FPGA.